Good morning, Dr. Sanus and everyone. Today our group will present our project title, Smart Elevator Control System for Multi-Level Buildings. The main purpose of this project is to design an 8-level elevator controller using digital logic component and simulate the complete system using this software. Our system mainly uses a 3-bit synchronous counter constructed with JK flip-flops, magnitude comparator, binary adders, and basic logic gate.
The project demonstrates how the digital logic concept learned in class can be applied to a real-world system. An elevator controller must remember its current flow, convey it with the selected destination, determine the correct direction, and stop exactly when the destination is reached. Instead of using a microcontroller, our design performs this operation using sequential and combination logic circuit.
The controller is designed for an 8-level building, from floor 1 to floor 8. Internally, the system uses 3-bit binary state from 000 to 111 base 2. State 00 represent floor 1 while state 111 represent floor 8. 3 bits are enough because 3 binary bits can represent 8 different states. The system also includes floor selection, direction control, door safety control, password authentication, and arrival indication.
Our case study is based on hotel emulator. First, the visitor select a destination for and enter the correct security password. Before the emulator can move, the door must be closed. The selected floor must be confirmed and start input must be active. The controller then compare the current floor with the desired floor. If the destination is above the current floor, the emulator moves upward. If the destination is below the current floor, the emulator moves downward. When both floor values become equal, the system stops and activates the arrive and door open indicator.
There are three main specifications in our system. First, the controller supports 8 floors from floor 1 to floor 8. Second, it uses a 3-bit counter which provides 8 possible binary state from 000 to 111 base 2. Third, the system includes safety interlocks. The elevator cannot move when the door input is inactive. The selected floor is not confirmed that the start input is inactive, the direction is incorrect, or the password is incorrect. Therefore, movement is only allowed when all required conditions are satisfied.
Our controller can be divided into the three main sections. The first section is the sequential module. It contains three JK flip-flop that form a seamless 3-bit up and down counter. This counter stores the current floor position. The second section is the comparator module. It continuously compares the current floor stage with the desired floor input. The third section is the control and enabling module. This section combines the door, set, start, direction, floor, equal, and password signal. In our final design, the code is connected directly to all three JK flip-flops. The enable signal control the J and K input instead of getting the clock directly. This prevent unwanted pause and skip flow.
Next, we will explain the technical architecture of the system. Design combines sequential logic for storing and updating the flow state, and combinational logic for comparison, direction, selection, authentication, display conversion, and safety control. Each subsystem performs a specific function, but all sections operate together as one complete elevator controller.
This slide shows the complete elevator controller built in DIT. The circuit is divided into several main sections. On the left side, we have three JK flip-flops and the basic logic gates. These components form the 3-bit signals up and down counter. The output Q2, Q1, and Q0 show the current internal flow state. In the middle of the circuit, we use a 4-bit magnitude comparator. This comparator compares the current flow with the desired flow selected by the user. The current flow value is connected to input A, and the desired flow value is connected to input B. If A is less than B, the current flow is below the desired flow, so the lift can move up. If A is greater than B, the current flow is above the designed floor, so the lift can move down. If A is equal to B, the lift has reached the selected floor and must stop. We also use two 4-bit adders. In the internal counter use value from 0 to 7, but the actual floors are numbered from 1 to 8. Therefore, each adder adds binary 0001 to the internal value. One adder is used for the current flow display, and the other is used for the desert flow display. This allows the displays to show the current flow numbers from 1 to 8. At the top right side, another 4-bit comparator is used for password checking. The user enters a 4-bit password, and the comparator compares it with the fixed password 1010. If the password is correct, pass OK becomes 1. The system then combines pass OK with the basic safety conditions. These conditions include door set start, the correct direction, and the current flow not being equal to the desert flow. When all conditions are correct, enable ADV becomes 1, and the lift can move. During testing, every manual clock phase moves the lift by 1 floor. When the current flow becomes equal to the desert floor, enable ADV becomes 0. The counter then stops at the selected floor. At the same time, the arrive and door open outputs become active. This shows that the lift have reached the destination safely. That is all for my part about the counter design and its circuit implementation. Now I will pass the presentation to the next speakers.
The main components used in this project are 3 JK flip-flop, 2 4-bit magnitude comparator, 2 4-bit binary adders, and basic AND or NOT gates. The first comparator is used for floor navigation. Input A represent the current floor, and input B represent the desired floor. When A is less than B, the destination is above the current floor, so upward movement is allowed. When A is greater than B, downward movement is allowed. When A is equal to B, the elevator has reached the destination and stops. So the second comparator is used for password authentication. It compares the enter 4-bit password with the fixed password 1010. When both values are equal, pass OK become 1. The two adders are used for the displays. because the internal counter values range from 0 to 7. Each adder adds binary 0001 to display the actual floor numbers from 1 to 8.
The slides show the main function performed by the logic gate. The trailing logic determines whether upward or downward movement is valid. The enabling network checks whether all operating conditions are satisfied. The display section converts the internal zero-based floor code into the actual floor number. The safely interlock section prevents movement when any required condition is not satisfied. The percentage shows how the represent the general distribution of the logic function is in the design. Together, this gate generate the main control signal, including DIR, OK, enable basic, and enable ADB.
Now I will explain the main counter design of our elevator controller. The current flow is stored by 3 JK flip-flops. Their output are called Q2, Q1, and Q0. Because we use 3 bits, the counter can store 8 different states, from 000 to 111. These 8 states represent flow 1 to flow 8. For example, 000 represents flow 1, 001 represents flow 2, and 111 represents flow 8. All 3 GK flip-flops use the same manual clock. This means the all 3 flip-flops update at the same time. Because of this, the counter is called a synchronous counter. The input U controls the movement direction. When U is equal to 1, the counter counts upward, so the lifter moves to a higher floor. When U is equal to 0, the counter counts downward, so the lifter moves to a lower floor. The counter is also designed to stop at the highest and lowest floor. At floor 8, the counter will not return to floor 1 when the lift is moving upward. At floor 1, the counter will not change to floor 8 when the lift is moving downward. In our first design, we used an AND gate to control the clock signal. However, this design caused a problem. During downward counting, the count sometimes skipped one floor because the clock signal was not stable. To solve this problem, we connected the manual clock directly to all 3 JK flip-flops. We then used the enable ADV signal to control the J and K inputs instead of controlling the clock. When enable ADV is 1, the J and K inputs work normally, and the counter can charge to the next floor. When enable ADV is 0, all final J and K inputs become 0. In this condition, the JK flip-flops keep the same state, even when the clock is preset. This makes the system more stable and prevents the lifter from skipping floors. This slider shows the complete
In conclusion, our project successfully demonstrates an 8-level smart elevator controller using digital logic circuits. The 3 JK flip-flop stores and update the current floor. The comparator perform floor comparison and password authentication. The adders convert internal state into human-readable floor numbers. The conjugate ensure that the elevator only move when all safety and authorization conditions are satisfied. The deed simulation confirms that the system can move upwards and downward, one floor at a time, stop at a selected destination, reject an incorrect password, and activate the arrival and door open indicators. Thank you for listening.